Physical science time. Okay. Oh, I do not want the red. Okay, today in physical science time we're going to be doing power and energy. Mr. Guy, you already did energy. You're saying to yourself, right? That we have already done energy, but we talked about some ways to calculate certain types of energy. What were the kinds of energy that we calculated previously? You know it. Kinetic energy and potential energy. In this case, we're going to be relating energy to power and power to work. Okay, so the first thing we're going to talk about is power. So just like the only thing that makes these lessons even a little bit confusing is that we already use the words work and power in just our normal linguistic usage to mean certain things, whereas in science they mean something completely different, right? In science we already talked about work means energy expended to move an object in a certain direction, right? To a force applied that moves an object that same direction. And power is how much time it has taken to do the work. Work compared to time. So for those of us who didn't do the lab and who are watching this on YouTube, we did a lab in here where you had your weight and you moved it up the stairs, right? In fact, you do that all the time, but in this case we measured the height of the stairs and we also measured one other thing. What else did we measure in the lab? How long it took, the amount of time it took to get to the top of the stairs. So we could calculate the work done by just applying our force, the force of our weight, over the certain distance of the height of the stairs, right? That was how we could calculate work. And we can also calculate power by telling how long that took. So who did more work? If we had twins, right? Imagine you got some twins, and they're both going all the way from the bottom floor to the third floor, and one's running and one's walking. Who did more work? Be careful. Just think about the things that work actually depends on.
The person walking.
Neither one, right? They both applied the same force, because they have the same weight, over the same distance. Neither one did more work. But it's easy to think that the one who went faster must have, right? But what you're actually thinking about then is power. And that's where this gets a little bit confusing, is that work and power mean different things than they do in our normal, regular usage. So power is calculated by work divided by time. So here we have an equation. What do we always do with an equation? Well, we write it down first, and then we have our variables. P is power, capital P. We had already talked about lowercase p. What was lowercase p? Does anyone remember? Momentum. Momentum was lowercase p. Capital P is power. What's capital W? Work. What's lowercase t? Time. Does anyone know what capital T might be? We haven't really talked about this, but it should be. What was it? Tarantula. No, not necessarily. Was it? Temperature. Tarantula's cooler. What do we measure work in? We just got done working with this, or we are still working on this. What do we measure work in usually? Joules. What do we measure time in? Seconds. So our unit for power is going to be equal to joules divided by seconds, right? Or we're going to have a special name for it, and it is watts, which is W. So be sure you keep these straight in your brain, because the variable capital W stands for work. The unit capital W stands for watts, which is a measure of power. Power. Okay, energy. We can calculate in the same way. So energy, do you remember how the units for energy and work were related? What was the unit we used for energy? Joules. What was the unit we used for work? So how are they related? They're the same. They're the same stuff. So energy in this case is power exerted over a certain time. Basically, we can just rewrite this exact same equation except having energy in for time. So in the same way we had power equals work over time, power also equals energy over time. So if we were actually solving for energy here, what would we do? to get energy by itself, multiplied by T. So PT equals E. So power supplied over a certain amount of time will give us energy. And power is measured also in watts. Well, we knew that already. Power is, P is power, once again, in watts. E is energy, oops, once again in joules, and T, again, is seconds. So what have we actually, sorry, T is time measured in seconds. What have we actually learned from this? Basically, we know how to calculate power, right? And we also know, and we had previously known, that energy and work are, they don't mean the exact same thing. For instance, can energy be exerted even if the object isn't moving in the same direction as the force? Yeah, energy changes all the time, right? Work has a more, we could think of it this way, work is a more strict definition of energy. In kind of the same way that, like, we say all the time, all rectangles are, or no, sorry, all squares are rectangles, but not all rectangles are squares, right? All work is energy, or involves a change of energy, but not all energy does work. Right? So let's do a couple of example problems with this real quick before we close, and where are we going to do them? Good question. I guess over here. It says, you do 900 joules of work in pushing a sofa. Have you ever done sofa pushing time? Yeah. Which is more fun, physical science time or sofa pushing time?
Physical science.
Physical science.
You're right. Sofa pushing time sucks. If it took 5 seconds to move this, although sofa pushing time is only 5 seconds. If it took 5 seconds to push the sofa, how much power did you use? So that should be pretty easy. What do we do first? First step, as always, is write the equation, which is in this case
P equals W over T.
Yeah, it would come out the same, but this specifically gave us a work being done. P equals W over T. Do we need to manipulate this? Nope. Already solved for power. Next step is substitute. What should I put in? W is 900 joules. How long did it take?
5 seconds.
5 seconds. Power equals 900 divided by 5 should be pretty easy. What is that? 180. 180 watts.
Watts.
That was kind of funny. 180 watts. Hey, have you ever heard of something like this before? You ever heard of this?
Yeah, in electricity.
Yeah, in electrical light bulbs, right? So basically, if you did the same amount of power and somehow converted all that sofa pushing to electrical energy, you could power a 180 watt light bulb for a second. Yeah, in fact, that's exactly what it means. Do you have questions about this? Could we have done the same thing given an amount of energy? Well, let's try one. I'm sorry, Dylan, what did you say?
How many watts are in a light bulb?
It depends on the light bulb, right? So light bulbs with higher wattage are usually brighter because it's telling how much energy they use per second, basically, which ends up being just how much energy, right? How much power. And so the more powerful the light bulb, the higher the wattage. So like a 1,000-watt light bulb, like the spotlight on the stage, is extremely bright, blind you if you looked into it. Right? Whereas the 100-watt light bulb that your mom uses to read at night probably isn't going to blind anyone. Okay, let's try another one. I'm just going to make up off the top of my head. We'll say that the toaster supplies 1,700 joules of energy every 10 seconds. Sure. The toaster supplies 700 joules of energy every 10 seconds. What is the toaster's wattage? This is a really sucky toaster. What should I do first?
Get a better toaster.
No, okay, so maybe instead of a toaster, something that doesn't need as much power as a toaster. The Game Boy Advance SP.
That's very
You guys do you even know what a Game Boy Advance SP is?
Yes.
That was my entire life when I was 11 years old. Anyway, I was 12 years old. Anyway, first step is write the equation. Power equals work divided by time, power equals, I specifically made this one so it would be energy. Energy divided by time. How much energy did the Game Boy Advance SP use? 1,700 joules every how often? 10 seconds. How much power was this device supplying? 170 watts. Which is actually, that's like a tricked out Game Boy Advance SP. Do you have questions about this at all? Do you think you can do this math?
You're wrong, I do have a question.
Bye.